Imagine boarding a train in the morning and stepping off 500 kilometers away before your coffee gets cold. No wheels, no rails, almost no air. For more than a century, engineers have chased a single dream: to delete friction and travel at the speed of sound on the ground. Three machines are racing to get there. Only one of them actually works at scale. This is Maglev versus high-speed rail versus Hyperloop. Meet the field. High-speed rail, steel wheels on steel track, the technology you can already ride in a dozen countries. Maglev, trains that float on magnets with no wheels at all. And Hyperloop, pods fired through a near-vacuum tube, the newcomer that promised to beat them both. Three answers to one stubborn question: how do you make a train go really fast? To understand the race, you have to understand the enemy: friction. A fast train fights two forces. First, the grip between wheel and rail, essential for getting moving, but above about 300 kilometers an hour, it starts to break down. Second, and far worse, the air. Aerodynamic drag rises with the square of your speed. Double your speed, and you quadruple the pushback. So engineers split into two camps. One said, get rid of the wheels. The other said, get rid of the air. Start with the one that's everywhere. High-speed rail is, at heart, just a train, but engineered to a knife's edge: dead-straight track, gentle curves, overhead power, and a long, aerodynamic nose. The bar to even call it high-speed is around 250 kilometers an hour. The best run at 350. Japan opened the first line in 1964, and today it's the backbone of travel across Europe and Asia. And don't call it boring. In 2007, a French TGV, on ordinary steel rails, reached 574.8 kilometers an hour. That record still stands. But the real superpower of high-speed rail isn't top speed. It's that the trains run on standard track. They glide off the high-speed line straight into the heart of the city, onto rails we built decades ago. China alone has laid 38,000 kilometers of it, more than the rest of the world combined. Now delete the wheels. Maglev, short for magnetic levitation, lifts the entire train off the track on a cushion of magnetism, often just 15 millimeters of air, and pushes it forward with nothing physically touching anything. There are two ways to do it. The German approach, used in Shanghai, pulls the train up toward the rail with electromagnets. The Japanese approach uses supercooled, superconducting magnets to repel it, floating the train a full 10 centimeters in the air. No wheels means no rolling friction, no wear, and an eerily smooth ride. And this isn't a concept. The Shanghai Maglev has carried passengers at 431 kilometers an hour every single day since 2003. And in 2015, Japan's L0 Maglev went further, 603 kilometers an hour, with people on board. The fastest a human being has ever traveled on rails. Remember that number, 603, because we're about to compare it to a promise. So why aren't we all riding Maglev? Because floating is expensive and lonely. A Maglev needs its own dedicated guideway, built to millimeter precision, and it can't share a single inch of track with anything else. It can't roll into the old downtown station. You have to build everything, end to end, from scratch. Even Japan is struggling. Its flagship Maglev line was meant to open in 2027. It's now slipped to 2034 or later. The idea of a train in a tube is far older than you might think. Back in the early 1900s, the rocket pioneer Robert Goddard sketched trains running through vacuum tubes. In the 1970s, engineers seriously studied vac trains that could cross continents in near silence. The physics was always tempting and always too expensive to build. Then, in 2013, one man dusted off the old dream and gave it a brand new name. Elon Musk published a white paper for what he called a fifth mode of transport, the Hyperloop. The idea: take a Maglev pod and seal it inside a steel tube pumped down to near vacuum. With almost no air to fight, the pod could, in theory, cruise at 1,200 kilometers an hour. Los Angeles to San Francisco in 35 minutes, faster than a passenger jet. The internet went wild. Dozens of startups and student teams raced to build it. The physics is genuinely clever. Drag depends on air density, so don't slow the air down, remove it. Pump most of the air out of the tube, and you cut resistance by orders of magnitude. The pod floats on magnets or a thin film of air, and linear motors built into the tube fling it forward. But there's a trap, called the Kantrowitz limit. Squeeze a pod through a narrow tube, and it starts to act like a piston, shoving a wall of air ahead of it. The fixes, a much bigger tube, or a compressor on the nose, are exactly where the costs begin to explode. So how fast has a Hyperloop actually gone, with a human inside? In 2020, Virgin Hyperloop ran the only crewed test in history. 2 passengers, a 500-meter track, and a top speed of 172 kilometers an hour. Let that sink in. The system that promised 1,200 managed 172. Slower than an ordinary bullet train, and slower than the Shanghai Maglev runs on its daily commute. The best any test pod has ever reached is around 460. And in 2023, the world's leading Hyperloop company simply shut down. Hyperloop isn't quite dead. In the Netherlands, a company called HART runs a European test center. In Germany, students at the Technical University of Munich keep breaking pod speed records. And in China, the state aerospace giant CASIC is testing a system it calls T-Flight, aiming, eventually, for 1,000 kilometers an hour. But all of it is still research. Short test tracks, small pods, no paying passengers. The dream survives. A working line does not. Let's put all 3 on one board. Top speed actually demonstrated. High-speed rail and Maglev, both above 500. Hyperloop, 172. Maturity. HSR and Maglev are carrying passengers right now. Hyperloop is still a prototype. And cost per kilometer. High-speed rail, around $25 million a mile. Maglev, 30 to 40. Hyperloop, north of 100 million, if it can be built at all. Speed, it turns out, has a price. There's a hidden cost, too. Energy. Above 400 kilometers an hour, Maglev is beautifully efficient, with no wheels and no rolling loss. But Hyperloop has to do something no train does. Hold a vacuum across hundreds of kilometers of tube, and keep pumping, day and night, forever. The very thing that makes it fast, empty space, is relentlessly expensive to maintain. Remove the air, and you spend a fortune keeping it gone. Why is Hyperloop stuck? Not because the physics is wrong, but because the engineering is brutal. You have to hold a near-perfect vacuum across a steel tube that expands and contracts with the heat of the sun, without ever cracking its seal. Puncture it at speed, and the air rushes back in like a hammer. You have to cycle passengers through airlocks, which throttles how many people you can move. And if something goes wrong in the middle, there is no easy way out of a depressurized tube. It's the Concorde problem. Technically possible, economically impossible. And here's the twist that decides the whole race. The hardest part of building a fast train was never the speed. It's the land. Every one of these systems needs a long, straight, uninterrupted right-of-way, and buying that, through cities and countryside, is a political fight, not an engineering one. This is high-speed rail's secret weapon. It doesn't need all new land. It runs on standard gauge track, so it can borrow the rails and the city center stations we already built. Maglev and Hyperloop have to start from zero. So who wins? It depends what you're racing for. If you want to connect a whole country affordably, today, high-speed rail wins, and it isn't close. If you want the fastest ride a passenger can actually buy a ticket for, and money is no object, that's Maglev, floating along at 600. And Hyperloop? For now, Hyperloop wins the imagination and nothing else. A brilliant idea, still waiting for a world that can afford it. Because the fastest train isn't the one that goes fastest on paper. It's the one that actually gets built. Free machines. One delivers every day. One floats for a price. One is still a promise. The dream of frictionless travel is very much alive. But for now, the train that wins is the one humble enough to share the tracks. Thanks for watching. If you learned something, stick around for more deep dives into how our world really moves.